We continue the vertex form of the quadratic function in the next few examples. The first one here is f of x is equal to 2 times x plus 1 squared minus 1. Last time we saw that the vertex form is given by a times x minus h squared plus k. So what we have here is f of x equal to 2 times x plus 1 squared minus 1. By direct comparison, we can see that a is 2 and h is negative 1 and k is negative 1. So since a is greater than 0, this would imply the parabola has a minimum. So all we need here is the vertex, and if we have the vertex, then we can easily graph the parabola because we know what it looks like. So the vertex is minus 1, minus 1, so it is right over here. And we just draw our usual parabola and we are done. So what we can see is there are no y values below negative 1. So nothing over here, and the entire function is going that way up. So the minimum y value that we can reach is minus 1. So the range here is from minus 1 all the way up to infinity. We never include infinity. So open paren there and bracket for negative 1. The domain of a quadratic function is always quite straightforward. It is minus infinity to infinity, because we can define this quadratic function for all real numbers. So moving on, this is an application of quadratic functions. So what we have here is a ball that is thrown upward and outward from a height of 6 feet. So we have our initial point, which is right over here. And the initial height is 6 feet. And we are throwing a ball upward and outward, so the ball is going to go like that, and eventually it is going to hit down, hit the ground. So what the problem wants to know is that particular point, which is the maximum, and the location where the maximum happens. So a certain distance outward from the initial point, you have the maximum. We would like to know what that maximum y value is, and the x value where the maximum happens. So that would be our first part, the maximum height of the ball and how far from where it was thrown does the maximum occur. So we want to find that and that. So all we have to do is to find the vertex, because the peak point here corresponds to the vertex of the parabola. And we know how to find the vertex. H is minus b over 2a, and k is the function evaluated at minus b over 2 times a. In short, it's simply f of h. So let's first find h. So we have the equation minus 0.8 x squared plus 2.4x plus 6. And the value of a would then be negative 0.8. The value of b is 2.4. And the value of c is 6. So by plugging in the values, h would be negative 2.4 divided by 2 times negative 0.8, and that would equal to 1.5. K, on the other hand, is f evaluated at h. In other words, f of 1.5. We plug it in the function that we have. And we get the answer to be 7.8. So that point right there, the vertex, is 1.5, 7.8. So the ball had gone up for about 1.8 feet from here, and it is going to come down and hit the ground soon, as it's moving toward the ground as after reaching the maximum height. So we'd have to find the horizontal distance from 0, the initial point, all the way up to the point where it hits the ground. So if you notice, that is the point where the function is becoming 0. So all we have to do is set f of x equals minus 0.8x squared plus 2.4x plus 6 equal to 0, and solve for x. As you can see, you can either use a quadratic formula, or you could use factoring if you can't factor it. Since we are seeing decimal values, it's actually easier for us to use the quadratic formula. We have the values of a, b, and c. So if we plug it in the quadratic formula, we will have minus 2.4 plus or minus square root of 2.4 squared minus 4 times negative 0.8 times 6 divided by 2 times negative 0.8. And that would give us a value of 4.62 and negative 1.62. Of course, x is the distance, and distance cannot be negative, so that is not a possible value. So the only possible solution is 4.62. So the distance from here all the way there is 4.62. So this is an application of a quadratic function. It sort of is related to physics. The next example number 4, is more of a number theory example. So what we have here is we have a set of pairs of numbers, and if we sum them, we need to get 16, but the number should give us the maximum product, the pair that has the maximum product. So how do we find it? First, we could call the numbers as A and B. Or X and Y. I'll call it X and Y. What do we know about the two numbers? If I add the pair of the numbers in the pair, I should get 16. So X plus Y would equal 16. That is given. And we would like to maximize the product. So the product here is X times Y. So you might wonder, well, I'm kind of stuck here because X plus Y is 16, product is XY. Where do we go from here? What you've got to realize is you've got to make a connection between B and A over here. Realize that X plus Y is equal to 16, which would mean Y is 16 minus X. So I could take y equals 16 minus x and plug it in the product. I'll have x times 16 minus x. And it may not look like a quadratic function, but if you FOIL it, you see that 16x minus x squared is what we would have. And if I rewrite that, I will have negative x squared plus 16x. And that is a quadratic function with a as -1 and b as 16. And obviously, you can notice that a is less than 0, therefore the vertex is a maximum. We want to find that vertex. We know the formula, h is minus b over 2a, and we have the value of b, 16, 2 times -1, we end up getting 8. So the value of h is 8, and the value of k is simply f evaluated at h. So our function f is 16x minus x squared, so 16 times 8 minus 8 squared. And we'd end up getting 128 minus 64, which is 64. So the value of the product is 64. This would imply x times y is 64, because the product is 64. So if we solve, we know that the x value here is the h, we get 8, and if x is 8, we'll have y to be 64 over 8, which is 8. So key things to note here: initial setup, x plus y equals 16, and the next step is to define xy as the product, which is our function. A crucial step here is to recognize that y is equal to 16 minus x, take that value and plug it in the product, and we'd end up getting that equation. So now you would realize that negative x squared plus 16x is a quadratic function with a equals -1 and b equals 16. And since a is 0, the vertex has to be a maximum. So we find the vertex, the h would correspond to the x value, and you take the value of h, you plug it in the function, you'd end up getting k. So k is not the number y, rather k is the product of x and y. So xy would equal 64, and since we know x is 8, we divide the equation by 8 after plugging in 8 for x, which would give us the answer for y as 8. So the two numbers are x and y, and the maximum product would be 64. Moving on. In this problem, you have 50 yards of fencing to enclose a rectangular region. We want to find the dimensions of the rectangle that maximizes the area. So that is my rectangle. I'll call the length as x, width as y, and we know the area of a rectangle is length times width. So that would simply reduce to x times y. just like the previous problem, you might look at that and say, well, seems like I'm stuck, I don't know where to go. If we go back and look at the previous problem, we sort of made a substitution using the condition a where x plus y equals 16. So we have a similar condition here also, which being we have 50 yards of fencing to enclose a rectangular region. In other words, the total amount that you can cover with fencing is 50 yards. In other words, I have x, y, which would mean that's y, and that's x. So that entire length around the rectangle has to be 50. In other words, the perimeter has to be 50. So x plus y plus x plus y, which is the perimeter, must equal 50. So what we have is 2x plus 2y equals 50. There is a 2 in common, so divide by 2 on both sides. X plus y would equal 25. So you can see that that is a condition very similar to the previous problem. So we could take that condition, rewrite it as y equals 25 minus x. And if you recall, we took that value, or that expression, y is equal to 25 minus x, and we put it back, or we will be putting it in the area function. So going back here, we'll have the area to be x times 25 minus x, which would give us 25x minus x squared. And 25x minus x squared is a quadratic function. And a is -1 and b is 25. As always, since a is -1, which is less than 0, the vertex, it should come to you. If it doesn't, think for a second, the vertex corresponds to a maximum. All we have to do is find the vertex, and we would know the maximum area that we can have for this enclosure. So h is minus b over 2a, which is -25 divided by 2 times -1. We have -25 over -2. We'll have -12.5. Oops, sorry, positive. Negatives go away, we get positive 12.5. K is obtained by plugging in the corresponding h value in the function. So 25 times 12.5 minus 12.5 squared. And recall that this is actually the value of the function evaluated at 12.5. So we're pretty much solving for the x-coordinate and plugging in that x-coordinate value in the function, which would give us the corresponding y value. In a practical sense, the x-coordinate here is the length and the y-coordinate is the width. And when you plug it in, you'd end up getting 156.25. You've got to be careful here. The reason being, this is the value of x, and that is the value of the area. Technically speaking, the maximum area, not the length, or in this case, rather width. Y, as we suggested earlier. So we know that the maximum area is 156.25, and if we want to find the width specifically, all we have to do is divide. We know area x times y would equal to 156.25. This would imply y equals 156.25 divided by x, which is 156.25 over 12.5. Which would give us 12.5. So key things in this problem is to recognize the initial step, which is right over here, and the step right here. In the previous problem, this was actually given to us, x plus y equals 25, but not as 25, but x plus y equals 16. In this problem, though, we had to come up with that expression, x plus y equals 25, using the information that's provided in the problem, that you have 50 yards of fencing to enclose a rectangular region. So I am going to go ahead and do these, even though it says now it is your turn. So both parts A and B have quadratic functions. So the first one here has A to be 2, B is minus 8, and C is 3. Recall, a standard quadratic function is denoted by ax squared plus bx plus c. Now you might wonder, or you might have wondered, where is he getting the a, b and c from? Directly comparing a to 2, b here to negative 8, and c here to 3. Since a is equal to 2, which certainly is greater than 0, this would imply vertex corresponds to a minimum. And we simply have to find the vertex. H is minus b over 2a. We have minus of minus 8 divided by 2 times 2. 8 over 4, we get 2. K is simply f of h. In other words, we find minus b over 2a and take that value and plug it in for x. So we get 2 times 2 squared minus 8 times 2 plus 3, which should be 2 times 4 minus 16 plus 3, negative 8 plus 3, which is negative 5. Since the vertex corresponds to a minimum, the parabola is open up of that sort, and that would be the vertex. And we know here that that value corresponds to 2, negative 5. So the lowest value that the function can take is negative 5. Therefore, the range has to be from negative 5 all the way up to positive infinity. So that negative 5 is the smallest value that the function can take, and we get that information from k, which is the y-coordinate of the vertex. The domain of a quadratic function is always straightforward, simply negative infinity to positive infinity. In contrast to the problem in A, which is f of x is equal to 2x squared minus 8x plus 3, in this part, in part B, we have the function in vertex form. We call it the vertex form because the form has the vertex in it, and we can obtain it by direct comparison. So, just as a quick recap, the vertex form is f of x equals a times x minus h squared plus k. And by direct comparison, I'm going to compare a with negative 2, negative h would be positive 1, positive k would equal positive 5. So what we have now is a to be negative 2, h is negative 1, and k is equal to 5. So in the previous problem, we had to find h and k using a, b, the values of a and b. In this problem, though, we don't have to do it because the quadratic function is in vertex form, so we can directly obtain the vertex from the equation itself. So since h is negative 1 and k is 5, the vertex here is minus 1, 5, and a is negative 2, which is less than 0. This would imply that the vertex corresponds to a maximum. And if a quadratic function has a maximum, it has to be of that sort. So the maximum point at the vertex there is negative 1, 5. So negative 1 is the x-coordinate and y is the maximum value that the function can take. So the maximum y value the function can take is 5. In other words, the function is capped at 5, so the maximum y value is 5. And it can take any other of y value below that, so negative infinity up to 5 would form the range, including 5 there. And the domain, as always, it is a quadratic function. The domain is simply negative infinity to infinity. Unless a restriction is specified in the problem itself, the domain of a quadratic function is always negative infinity to infinity. So things to note in this particular lecture is the vertex form, which is a times x minus h squared plus k, recognizing that the vertex would either correspond to a minimum or a maximum. And we did two problems, application ones, where we had to find the maximum area and the maximum product, and both of those problems we took the word problem, we converted it to an equation and we obtained a quadratic function. We made use of the quadratic function to find the vertex. Then we realized that the vertex corresponds to a maximum. So we get the numbers for x and y, for instance, in example 4, using the product x times y equals 64. In example 5, we know that x times y is the area, and the maximum area is 156.25. We use the value of h to find k. 156.25 divided by 12.5 is 12.5. I do have to stress this point again, that oftentimes, since this is a y coordinate, students might conclude that the value of y is 156.25. In other words, the width of the rectangle is 156.25. But that is not the case, because here k is the value of y, where y is the area and not the number. If you want to avoid confusion, you could rather call x and y here as a and b, or L and W, which would take you away from the variables x and y and avoid confusion that way. And we did another problem, which is using a quadratic equation, but not in vertex form, rather the standard regular ax squared plus bx plus c form, and we use that to find the vertex, the maximum point, and we also found the point where the function crosses the x-axis, in other words, the zero of the function. And in this example, where we throw that ball upward and outwards from a height of 6 feet, when the function crosses zero, it simply means it is hitting the ground in a application sense. So that would be a good stop for this lecture, and until next time.